Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. Tempests of the Cosmos. Unveiling the solar system's stormy secrets. In the vast expanse of our solar system, storms are not merely weather phenomena but grand spectacles of nature that reveal the dynamic and often violent processes shaping the celestial bodies we call planets. These storms, varying in size, duration, and intensity, offer a window into the atmospheric conditions and the underlying physical laws governing these worlds. The solar system, with its diverse array of planets, each hosts its own unique weather systems, where storms play a pivotal role in their atmospheric dynamics. On Jupiter, the largest planet in our solar system, storms are not just frequent but also monumental. The most famous among them is the Great Red Spot, an anticyclonic storm that has been observed for over 300 years. This storm, which is larger than Earth itself, swirls in the planet's southern hemisphere, its reddish hue possibly due to complex chemical reactions involving sulfur and phosphorus. The Great Red Spot is not alone. Jupiter's atmosphere is dotted with smaller storms, white ovals, and brown spots, all part of a continuous weather system where winds can reach speeds of up to 644 kilometers per hour. These storms are driven by the planet's intense internal heat, which radiates outward, interacting with the solar wind and Jupiter's rapid rotation to create a maelstrom of atmospheric activity. Moving closer to the Sun, we find Venus, shrouded in thick clouds of sulfuric acid, where the atmospheric pressure is 92 times that of Earth's. Here, storms manifest differently, with the planet's entire atmosphere caught in a superrotational wind pattern, circling the planet in just 4 Earth days. This rapid circulation leads to a perpetual global storm, with lightning and thunder echoing through the thick cloud layers, a testament to the extreme conditions on Venus. The storms here are less visible than those on Jupiter but no less intense, with wind speeds reaching up to 360 kilometers per hour, creating a weather system that is as enigmatic as it is hostile. Mars, though much colder and with a thin atmosphere, also experiences storms, albeit of a different nature. Dust storms on Mars can grow from local disturbances into global phenomena, engulfing the entire planet in a veil of dust that can last for months. These storms are driven by the temperature contrasts between the Martian day and night, lifting dust into the atmosphere where it absorbs sunlight, further heating the air and intensifying the storm. The 2018 global dust storm was so massive it obscured the surface from view, a dramatic demonstration of how even a planet with minimal atmospheric pressure can host weather events of planetary scale. Saturn, with its majestic rings, is another giant where storms carve the atmosphere into complex patterns. The most notable recent storm was the 2010 to 2011 Great White Spot, a massive storm that encircled the planet's northern hemisphere, visible even from Earth with amateur telescopes. This storm, like those on Jupiter, showcases the planet's internal heat and dynamic atmospheric circulation, where ammonia crystals and methane contribute to the storm's visibility and character. Saturn's storms are part of a cycle, appearing roughly every 30 years, coinciding with the planet's equinoxes, suggesting a deep connection between solar heating and atmospheric dynamics. The gas giants and terrestrial planets each tell a story of how storms are not just isolated events but integral to the planet's atmospheric evolution. On Earth, storms are part of the water cycle, driven by solar energy. But in the solar system, each planet's unique composition, heat sources, and atmospheric chemistry give rise to storms that are as diverse as the planets themselves. These storms, from the colossal cyclones of Jupiter to the dust devils of Mars, paint a picture of a solar system alive with activity, where weather is not just an event but a continuous narrative of cosmic proportions. In the outer reaches of our solar system, the ice giants Uranus and Neptune present a different narrative of storm activity, one deeply influenced by their unique compositions and far greater distances from the Sun. Uranus, with its peculiar sideways rotation, experiences storms that are less frequent but no less intriguing. The planet's atmosphere, composed largely of hydrogen and helium with a touch of methane, gives it a pale blue color, but it's the occasional storm activity that captures attention. Observations have revealed large dark spots on Uranus, transient cloud formations thought to be cyclonic storms similar to those on Neptune. These storms, while less understood due to Uranus' distance and less frequent visibility, hint at deep atmospheric dynamics, with methane clouds playing a significant role in their formation and appearance. Neptune, the farthest gas giant from the Sun, boasts some of the most dramatic and visually striking storms in the solar system. The Great Dark Spot, observed by Voyager 2 in 1989, was a storm similar in size to Earth, with winds twice as fast as a Category 5 hurricane on our planet. Unlike Jupiter's Great Red Spot, Neptune's storm systems are more transient, appearing and disappearing over decades, suggesting a dynamic atmosphere where storms are perhaps driven by both internal heat and solar energy in a complex interplay. The observation of high-speed equatorial winds and the rapid changes in storm structures on Neptune underscore a world where weather is as enigmatic as it is beautiful, with methane clouds coloring the storms in shades of blue. Transitioning from gas and ice giants to the smaller, rocky bodies, the dwarf planet Pluto offers an unexpected perspective on solar system storms. Despite its small size and distance from the Sun, Pluto's atmosphere, when heated by solar radiation, expands, leading to wind patterns and, potentially, storm activity. Observations from New Horizons in 2015 hinted at haze layers and wind streaks, suggesting a dynamic, albeit thin, atmosphere where nitrogen and methane ices could participate in weather phenomena. While not storms in the traditional sense, these activities on Pluto illustrate how even the smallest and coldest bodies can exhibit atmospheric dynamics, challenging our understanding of what constitutes weather in the solar system. The moons of these planets, especially those orbiting gas giants, also experience their own forms of storms. Titan, Saturn's largest moon, with its thick, nitrogen-rich atmosphere, has methane rain and possibly methane storms, creating lakes and rivers on its surface. The weather system on Titan, while operating on a methane cycle similar to Earth's water cycle, showcases how storms can exist in environments vastly different from our own, where methane clouds gather and precipitate, shaping the landscape in a slow, geological dance. As we consider these diverse storm systems across the solar system, from the towering cyclones of Jupiter to the methane-driven weather on Titan, we see a reflection of the complexity and beauty of planetary science. Each planet and moon, with its unique chemistry, distance from the Sun, and rotational characteristics, contributes to a tapestry of atmospheric phenomena that not only challenges our understanding of weather but also enriches our appreciation of the universe's diversity. These storms are not merely disturbances but are part of the very fabric that defines the character of each celestial body, telling stories of energy, matter, and motion on an interplanetary scale. The solar system's storms, as diverse and dynamic as they are, also serve as natural laboratories for understanding not just planetary science but also the fundamental physics driving atmospheric phenomena. Each storm, from the ephemeral to the enduring, provides insights into fluid dynamics, thermodynamics, and the interactions between planetary bodies and their environments. On Earth, our understanding of weather patterns, including storms, has significantly advanced with the study of other planets. The cyclones on Jupiter, for instance, have parallels with terrestrial hurricanes, offering a broader perspective on how such systems form, evolve, and dissipate under different conditions. This comparative planetology has implications for climate models, weather prediction, and even the search for life, as extreme weather conditions can influence habitability. The Sun itself, though not a planet, plays a crucial role in the storm dynamics across the solar system through solar wind and solar flares. These solar phenomena can interact with planetary atmospheres, influencing space weather and, by extension, the storms we observe. On Earth, solar storms can lead to spectacular auroras but also disrupt satellite operations and power grids. On Mars, solar wind strips away the thin atmosphere, affecting the dust storm's intensity and duration. This interaction between solar activity and planetary atmospheres underscores the interconnectedness of solar system weather, where events on the Sun can ripple out to affect conditions billions of kilometers away. Comets, too, contribute to our understanding of storms in unique ways. As they approach the Sun, comets develop tails and comas, which are essentially temporary atmospheres where dust and gas are blown away by solar radiation and solar wind. These events, while not storms in the traditional sense, mimic atmospheric behavior, providing insights into how particles move in gaseous environments under solar influence. Moreover, the study of storms across the solar system has implications for future space exploration and human settlement. Understanding the atmospheric conditions, including storm systems, on other planets and moons is crucial for designing missions that can withstand or even exploit these conditions. The harsh environments of Venus or the dynamic weather on Mars pose significant challenges but also offer opportunities for scientific discovery and technological innovation. In the broader cosmic context, the storms of our solar system are but a microcosm of what might occur on exoplanets. The insights gained here help scientists predict and understand weather on planets orbiting other stars, where conditions might be vastly different, potentially including water vapor storms on terrestrial planets or silicate clouds on hot Jupiters. In conclusion, the storms of our solar system are not merely weather events but are emblematic of the dynamic, evolving nature of planetary bodies. They are a testament to the complexity of atmospheric science, where physics, chemistry, and celestial mechanics converge to create phenomena of beauty, power, and scientific intrigue. As we continue to explore and understand these storms, we not only learn more about our own planet, but also about the potential for life, the limits of habitability, and the universal processes that shape worlds, whether they are close to home or light years away.